All right, we are on day 15. We've got almost all of the stars except for day 12, part 2, which I'm still working on. So let's take a look at what day 15 has. You find a door under a large sign that says Lava Production Facility, next to a smaller sign that says Danger, Protective Equipment Required. Before you begin, please be prepared to use the holiday ASCII string helper algorithm, Appendix 1A. You turn to Appendix 1A, and the reindeer leans closer with interest. The hash algorithm is a way to turn any string of characters into a single number from 0 to 255. To run the algorithm, start with the current value of 0, then for each character in the string, starting from the beginning, determine the ASCII code for the current character of the string. That should be pretty easy for us. Increase the current value by the ASCII code, set the current value to itself multiplied by 17, set the current value to the remainder of dividing itself by 256. So add a bunch of stuff up and then modulo. I guess remainder is a specific one, but I think we're going to use percent. After following those, the current value is the output of the hash algorithm. So to find the result of running the hash algorithm on the string HASH, current value 0, ASCII code, yada, 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 bunch of division. So the result of running the hash algorithm on the string hash is 52. The initialization sequence, your puzzle input, is a comma-separated list of steps to start the lava production facility. Ignore Lunu line characters when parsing the initialization sequence to verify that your hash algorithm is working. The book offers the sum of the result of the running... The book offers the sum of the result of running the hash algorithm on each step in the initialization sequence. So rn1 cm minus qp equals 3, and the sum is 1320. We don't have the initialization number on the page, so run the algorithm. What's the sum? The initialization sequence is one long line. Be careful when copy pasting it. So we got this, split by comma, iterate over everything, iterate by cars, pull the algorithm on everything, be done. Just create day 15 uno cinco. So there's our input. I mean, I guess we could write a parser today. That would be interesting at least. It's any alpha or any ASCII character, right? So I guess we just split on comma today. 1320. So input dot split comma dot map. I guess this could be a dot fold at some point, but dot map hash dot cars. I guess this is a fold. We start off with 0. We have an accumulator. We have next car. And then what's the actual algorithm? It is ASCII code it, multiply by 17, divided by 257. So accumulator plus next car as U8 plus, or actually divided by 256 plus mod 256. So that's our next answer. That folds up. This collects, this sums into a U size, and I think that's it. We sum them all up, right? That's the right option. 11 steps, sum of the results. Map, sum, okay, num.toString. I think that's it. Sum into U size isn't happening. What is going on there? Iterator item changed to U8 here. I think this can just be U size. I think the conversion is the same, but we'll find out in a second here. 3416. So that dot inspect our value, debug v, and then what do we get? Looks like our numbers are too high. 334, 253. Rn equals 1 becomes 30. Oh, right. It's at least this. The parens need to be like that. Set the current value to itself multiplied by 17. Oh, did I forget that part? Accumulator plus next car times 17 mod 256. Is that the right? Okay, part 1 test pass. I just forgot the 17. So accumulator, the outer parens are useless here. So accumulator plus next car as U size multiplied by 17 mod 256. Oh, I was running the wrong day. Damn. Well, we got our gold star. All right, well, let's get rid of all of this other debug stuff. How did I get onto day 15 or day 14? Oh, well, I guess I'm just getting tired. All right, you convince the reindeer to bring you the page. Page confirms that your hash algorithm is working. Book goes on to describe a series of 256 boxes, numbered 0 through 255. The boxes are arranged in a line. Starting from the point where the light enters the facility, the boxes have holes that allow light to pass from one box to the next all the way down the line. Inside of each box, there are several lens slots to keep a lens correctly positioned to focus light. Passing through the box, the side of each box is a panel that allows you to open, insert, or remove lenses as necessary. Along the wall running parallel to the boxes is a large library containing lenses organized by focal length, ranging from 1 to 9. We also get a label printer, hash map, sequence of letters that indicate the label of the lens on which the step originates. The result of running the hash algorithm on the label indicates the correct box for that step. Label will be immediately followed by a character that indicates the operation to perform, either an equal sign or a dash. If the operation is a dash, go to the relevant box and remove the lens with the given label if it is present in the box. Then move any remaining lenses as far forward in the box as they can go without changing their order, filling any space made by removing the indicated lens. If no lens in that box has the given label, nothing happens. If the operation character is an equal sign, it will be followed by a number indicating the focal length of the lens that needs to go into the relevant box. Be sure to use the label maker to mark the lens with the label given in the beginning of the step so you can find it later. There are two possible situations. If there's already a lens in the box with the same label, replace the old lens with the new lens, remove the old lens and put the new lens in its place, not moving any other lenses in the box. If there is not already a lens in the box with the same label, add the lens to the box immediately behind any lenses in the box. Oh, multiple lenses in a box. Don't move any of the other lenses when you do this. If there aren't any lenses in the box, the new lens goes all the way to the front of the box. Here is the contents of every box after each step in the initialization sequence above. Rn equals 1 is what? Put R in the box, put N in the box. Cm minus means take C and M out, or is Rn the name of the label? Are each of these names? Okay, it's label and then operation. All 256 boxes are always present. Only the boxes that contain any lenses are shown here within each box. Lenses are listed from front to back. Each lens is shown as its label and focal length in square brackets. To confirm that all the lenses are installed correctly, add up the focusing power of all the lenses. Focusing power of a single lens is the result of blah, 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 blah. It's a lot of rules. All right, so I guess we parse this in first. I'm going to parse this into an instruction set because I don't see how I'm going to keep track of it otherwise. There's so many rules. Okay, the only way I'm going to keep this together in my head is if I write a parser. There is no other option for me. So we're going to write the parser. What are we calling each of the things we need to operate on? I'm going to call them instructions. I don't know what they're going to be. So for each instruction, then, there's going to be a hash as a string slice, or I guess the label is a string slice. The hash is a usize. The operation is an operation, which is either insert or remove, right? I think equal sign or dash. Dash is a removal, equals is an insertion. And then is there another value we need? We've got the label, the hash, the operation, and I guess the focal length, which is actually probably a U8, but I think the focal lengths are U8s, they're 1 to 9. So let's keep that small, I suppose. The hash is also technically a U8, but we need to be able to calculate it. So I'm going to make that a U size to be easy to deal with, I think. Well, let's make it a U8 because it's 0 to 255, right? So we either have an insert or a remove. We always have a label. We always have a hash. And if we have an insert, then we have the focal length to insert. Derive debug, add our lifetime here, add our lifetime here. This is not an enum. This is a struct. This is instruction. Okay, so to parse an instruction, is alphanumeric enough? That is only a subset of the values. So I guess we can take until equals, right? It's either going to be equals or minus, and I don't think we use those. I think these are all alpha. Yeah, actually, I think all the inputs are alphas. So we can do alpha 1 and then alt and then the number if it exists. So we want the label here, and the operation is going to be minus or equals, and then the focal length is going to be an opt U8. We're going to have input. And I think we can actually match on the focal length because if we parse a focal length, then we have to have the equals. So actually parsing this operation isn't even useful for us because it's just a separator because we will never have a minus with a number. So we either insert or we remove, and then we have to calc hash on the label and put our operation there. So we need calc hash. We need to bring in a couple things into scope. These need to take the input, and then we need our calc hash function from part 1. Which is this, which honestly I can just drop right here if I want to. So I'm doing this label cars fold to get the value. We're working on U sizes inside of the fold. We're going to try to squeeze that U size down into a U8, and it's either going to work or it isn't. And if it doesn't work, we should resolve to a U8. So we will at least know if something goes wrong here. Now this could be an error that we propagate through this parser, but we're gonna have enough to do today. So if we get a separated list here, separated by comma, right? I guess we complete car this. Then we have our instructions. And here what we wanna do is instructions, input, expect, should parse, to do. Okay, so now we have a vec of instructions to work on. And that'll help keep it clear in my head. Let's get the test value. I realized I didn't grab that. So this focusing power is going to be 145. Well, that's 145. And then our input's going to be the same, right? So that's this. Let's make sure I am testing the right day. Quite a few extra processes here that I'm going to just nip off right now. So run day 15 part 2, and we have a failing test, which is great. That's what we want. And now we need to do our whole fold down. We need to keep this in what? 256 boxes, I believe, was the 0 to through 255. So we need 256 boxes. I am going to initialize that. What are we going to store in these? The lenses, probably, but what is the lens structure going to look like? This is going to be RN1. So the label and the focal length. So label and the focal length. We will need a couple of derives on this immediately, like debug. Eq and partial eq makes sense. The labels and the focal lengths will have to match. This is going to be lens, I guess. I forget what we're calling what we put in here. So we have lens here. We have 256 of them in boxes, and then we need to operate on all of them. At the end of the day, we just have a bunch of boxes, right? So we need to iterate over all the instructions. I guess we fold that. We start with boxes. I want to call this boxes while I'm working on it. And then we've got the next instruction. We're going to have to turn an instruction into a lens. So let's do impl from instruction for lens. I think this all needs the lifetime specifications. We're just saying that the lifetime of instruction and the lifetime of lens, or the ones that are used there, are going to be the same. Fill struct fields. This is going to be value.label. I guess this is technically going to be TryFrom. We're just going to make the error a string for now because we don't really care. We're just going to unwrap it anyway right now. Fill struct fields, value.label. Right, we're going to be in an operation here. So if we're in insert, we can turn it into a lens. If we are not, then we cannot, which is why this is going to be okay. Invalid conversion for value.label. This is just going to be a format. So we'll return a string error if we do have an error, and otherwise we are going to return a lens. This to do is going to be the focal length. So we used TryFrom here because there's a concept of failure. We could fail converting from an instruction to a lens. If we did something wrong and we're trying to convert an instruction that it has an operation of remove, then we need to know that. Because to do an insertion, we have to have a focal length, which means that we can't be operating on remove in the wrong fashion. TryFrom for instruction, or from instruction to lens, will tell us if we try to do that. So vec found unit. That's because we haven't finished our fold down here. Of course, we'll be returning boxes. So we'll match on next instruction, right? I guess we don't need to match on next instruction. We need to match on next instruction.operation. I guess we can just do the TryFrom. It's not actually implemented for shared reference, so we could do that. We're gonna have shared references here anyway, which means that this is a shared reference, and we can create a lens using that shared reference correctly. And now we have everything working out. So lens from, if we have a lens, we need to do something with it. Otherwise, we need to remove, right? It's either insert or replace or remove. Boxes is going to have to be mutable. So subtraction or removal means go to the relevant box, which is defined by the hash value, remove the lens with the given label if it is present in the box, then move any remaining lenses as far forward in the box as they can go without changing the order, filling any space made by removing the indicated lens. So I think if we're going to store everything in vecs here, that remove is going to be boxes next instruction dot hash. That'll be a vec. I can't name things box. Well, I can name things box. It's just a little awkward. R hash box equals this. This has to be as usize because it will be a U8 when it comes in, and this will be a mutable reference to that vec. So R hash box, I guess remove uses an index, which we don't know the index of. Retains only the elements specified by the predicate. I think retain is what we want here. It would be nice to do a remove, but we don't know the index here. So R hash box dot retain lens not equal, or lens dot label not equal next instruction dot label. I think that's all we need to do there. Because the elements are visited exactly once in the original order, external state may be used to decide which elements to keep. Cool. And we get the same order out. I don't think we have a better function to use here. And then our other option is we either replace or we insert. So we do have a replace or a swap, I guess. So we need to find index before we do this. Swap remove isn't quite what we want though. I mean, we can do just mutation here. I was hoping to get swap. Swaps two elements in the slice. I don't want to do that. We could just use standard mem swap. I kind of expected that there would be a function that we could use on vec that would kind of like call this for us. I think replace is actually what we want. Mem replace. So if we have a lens, then this is insert or replace. So we want boxes dot position of the lens. I guess we need to iter here. We match on index. If it's some, we replace. I'm going to call that cell. If it's none, we insert, replace. I'm going to call this cell index, I guess, or box index. Box index is probably better. So boxes index, standard mem replace. We can get mute on the index. Oh, that's why I wasn't using the right one here. Source and destination. And this is, wait, why am I iterating over boxes here? This is boxes next instruction hash as usize. That's what we need. And then next instruction hash as usize, index in that box, replace. We don't use this value, which is fine. So this would be a lens, but I'm going to do underscore here to just not use it, not worry about it. And otherwise it's boxes next instruction dot hash dot push lens, right? This has to be as usize because that's a U8. And otherwise, I think we're good. And then what is the value we have to calculate? Focal length power. Add up the focusing power of all the lenses. So this is 1 plus the box number. Is the box number 0 or 250? Or like 0 or 1? I guess it's 0 here, right? Box 0. That's useful. Wait, no. RN1. Oh, that's confusing. RN1 is in box 0. Okay. So it gets a point for being in box 0, a point for being in the first slot, and a point for the focal length. 1 plus the box number, slot number, focal length. So boxes.iter.map r hash box. And we have to do this for r hash box because box is an identifier, which we'll talk about in the deep dive. Sum this into usize, and then we'll return okay result.toString. And each box then, r hash box dot iter dot numerate, because we need the position dot map lens, right? Usize and lens. So this is position and the lens itself. Oh, that's not, yeah, that's the position of the lens. We also need the box. So box, position, and our box, because we need to enumerate up here. Box, iter, enumerate, position. So we have box position first, right? Box position plus 1 times position times lens dot focal length. And the focal length is as usize. And our sum is, I guess this is flat map because I didn't collect the inner iterator. This is boxes.iter, which probably has a move deal borrowed here after move. We can into iter to consume this if we want to. Or did we move this way back up here at 89? Boxes. We're folding over boxes. Oh, because I don't, let's call this filled boxes so that we have a little bit of a differentiator. So filled boxes into iter, we're taking ownership, flat mapping, our box into iter. I guess it doesn't really matter whether we into iter here. We need the move here because the enumerate's coming in. So for here, we're doing everything. We're getting 0. Why are we getting 0? Match index, find lens equals lens. This is the lens from the next instruction. Oh my, I definitely just did that. How did I not get warned about that? I feel like that should be a compile error because I'm doing lens equals lens and I named it lens. So why would it? Oh, Clippy would have failed. I wasn't running Clippy. I chose to skip. Okay, so I have this command here, right, in the just file, and it's just work day whatever. And it's been running benchmarks a little bit early for me lately. So I started to move away from using it a little bit because I've been starting to get a couple of like errant processes and I wasn't really sure why and I didn't want to debug it. But because of that, I wasn't running cargo Clippy, which is like the very second step or something like that. We check here, watch, check, we lint, and cargo Clippy has very good information most of the time. I will say it's not always accurate, but in this case, equal expressions as operands to equals means this would have gotten caught by Clippy had I been running it ahead of time. So 1 vote for cargo Clippy, because this is the thing that we would need to do. And then we add the ampersand here because it needs to be a reference, and we can get rid of these boxes. It still looks like we have a test failure, but that at least is now a debuggable test failure. 154 and 145, just make sure I copied the right number in here. 145 is correct. So let's do a debug here, right? And now we get the result for each lens, 0 to 20, 48. 0 to 20, 48. So these numbers are definitely wrong. Box position plus 1, right? So 0 plus 1 times being in the first slot. It's times 0, isn't it? That's annoying. Off by uno. Okay, so now 1, 4, 36, 40. We're still wrong. 1, 4, 36. So RNCMOT, RNCMOT, ABPC, ABPC. And then it does OT again. So that's wrong. So our logic is at least a little wrong. I don't see this ever happening. We never replace because index is never accurate because these need to compare on label. Yikes. Now our test is passing. Okay, couple of little small logic errors effectively. Get rid of this again. We don't need that. We don't need this. Don't need that. Don't need that. Don't need these. Okay, so our test is passing. Part 2, we get our number and we get our gold star. Sweet. Took me a little longer than it should have today. I made a couple of really silly logic errors, really silly, like using the wrong if expression, that kind of stuff. Nothing even wrong in the actual logic. I ran the wrong command at the beginning for the wrong day a couple times and was really confused as to why I was getting the wrong answer. Okay, so we've got everything cleared up now. Let's cover what we wrote. So part 1, we get this input down here. That is a couple of ASCII characters in a row, separated by commas. So we split on commas, we map over those. Each of those is given a hash, so it's rn equals 1, cm minus. Turn those into characters, fold them. We do a little bit of math. We do the character that we're given. So this is a char type in Rust, which we can do as usize. So we need to add the accumulator or whatever we had, plus the ASCII value of that character, multiplied by 17, and then we mod it with, or get the remainder of dividing it by 256. This all gives us our numbers. We sum those up. For part 2, there's a slight difference in the way we need to interpret these. So this is now the beginning is our hash value. So it's just Rn or just Cm. Equals or minus represent the operation. And then actually the operation almost doesn't need to be there because we'll either have a lens number or we won't. So the equals and minus, fundamentally, we don't actually even need those for this parsing to work. But I chose to bring this up into a set of enums. So we have an instruction enum and an operation. So we parse this out. The label is going to be that hash string. The hash is going to be the score we calculated from the part 1. And the operation is going to be whether to insert a lens focal length or remove it. When we do these insertions, we are going to be inserting lenses that have labels and focal lengths. I chose to do that with this struct. We implement TryFrom Instruction, or TryFrom a shared reference to an instruction, because that's actually what we end up having for lens. Now you can implement this for multiple different sort of references, right? If we have a shared reference to an instruction or we have an owned instruction, those can both be implemented. And actually, if we have one, we can implement the other in terms of that. So if we have a shared reference TryFrom, we can use the TryFrom for the shared reference if we have an owned value as well. So we just kind of get that other implementation for free. We set our associated type here. So this is an error that is associated with the implementation of TryFrom. So if we go look at TryFrom, the trait definition defines some type and some associated error. This is called an associated type. This is the error that's associated with the TryFrom implementation for type T. So we're doing TryFrom shared reference to instruction, and we're implementing that trait for our lens struct. We are required to implement the TryFrom method right here, which is not selecting. There we go. And to do that, we have to define some kind of error to be our error value for our result return type. Our result, if you forgot, is OK and error. It's an enum. It's either one of these two. So our error can be anything here. Typically, when you deal with errors, it's a whole process. For us, we chose to just go with a string because we're not really using it much later, but we do have to define it. So this TryFrom function takes that shared reference to the instruction that we told it we were going to implement and returns either self, which is a lens, or self error, which is the trait implementation's associated type. So self error in this case is error. In this case, we match on value.operation. If it's an insert, we have a focal length, and this successfully converts into a lens, which we create here and return the ownership of. If it's remove, we can't do the conversion, which is why we're implementing TryFrom and not from. We then choose to parse all of those inputs as full-on instructions. So in this case, rn equals 1, cm minus. So everything's separated by these commas, which means that we're doing a separated list 1 based on this comma here. And our parser for parsing out each of the individual pieces is instruction. Instruction then grabs alpha 1 because we only have alpha characters for the hash labels. Our sort of separator here is either minus or equal sign. I did parse this out and leave it here, but we actually don't even need to. We do need to skip over it for the parser, but it could be used as a separator because minus and equals actually are not fundamentally interesting for our parser. So we actually don't even use them because if we can parse a focal length here, then we have either an insert or an like update or a replace, right? And insert and replace aren't differentiated. They're the same value, as it were, the same return type here. Whereas remove just won't have the focal length because it will remove the label or the lens labeled the label rather than a lens with a specific focal length. So this middle thing doesn't even matter at all. We don't need it. We either have a number or we don't. Opt is what lets us run this U8 parser and get a value back here, whether it succeeds or fails. So this focal length is an option because of this opt. So if U8 fails, we don't have one. If it succeeds, then we do have one. We match on that to determine the operation, and then we return our instruction. In this case, we take the label, so that's like RN, CM, QP, whatever. We take the cars, we fold over it using the same like scoring calculation we used in part 1, and we try to turn that into a U8. So if we look at the types here, label cars fold, we're dealing with U sizes inside of the fold because we don't know how big this is going to get. And then when we're done with that, we know we should have a U8. So we use try into to turn a U size into a U8, which will fail if we have a number that's too big. We never do, so it always succeeds, but it's good to like make sure that we have this check because if we do something wrong, this is an early termination for us. So we build up that instruction, we have a vec of instructions, and then we need to process them. So we parse our instructions out. I am storing that in a variable called ins. We construct a vec of lenses, of which all of the vecs are empty. And in this case, I used collect vec here, but I actually don't because I wrote the type out anyway. Collect vec comes from itertools, not super important. Same thing as collect, just into a vec. So we get 256 of these empty vecs, right? Then we iterate over each of our instructions, folding them down. So we have many instructions, and we need to turn that into a single value, which is our vec of boxes. So we use our boxes, our empty boxes, as our initial value. And then we have this callback that will get called for every instruction we need to process. For every instruction, we'll update boxes and then return it at the end. That's all the way down here. So in our case, we could match on next instruction.operation, but we actually don't need to because this lens will only succeed in becoming a lens from that instruction if we have to do an insertion. So if we have a lens to do something with, then we will either insert or replace. And if our conversion fails, then we have to remove that label from the box. Removal is a little bit easier to talk about. We get a mutable reference to the inner box. So the boxes is the huge vec, and our hash gives us the index into which box of lenses we're dealing with, which we store in a variable called box. Now we have to put the hash here because box is a registered keyword in Rust. A box is a thing. We haven't talked about this yet. It's not really relevant, but in the future, or actually right now, depending on what you're doing, this syntax exists. It looks like that feature was actually phased out now that I'm looking at it, kind of hilariously. We do have box : new, but you used to be able to write box like this to box a value, but I guess that's not a thing anymore. Happened over the last year or so while I wasn't paying attention. So interesting. Anyway, box is a keyword, and if you want to name a variable a keyword, you need to use our hash in front of it. So instead of writing this like box, which you can see highlights as a keyword, we have our hash box. So we get a mutable reference to the box inside of the box's vec, and then we run retain on it. In this case, that retains only the elements specified by the predicate. So in this case, anything that is true gets kept. Anything that is false gets removed. So if the labels are different, then we keep this. If the labels are the same, then we remove it. And that's mutating, so we don't really need to do anything else. If we need to insert or replace, we can try to find to see if there's a current lens label in the box that we're looking for. So boxes hash is our index into the box that we want. If we iterate over that and look for the position of a lens that matches the label that we're trying to insert, then this is going to be a replacement. Otherwise, it's going to be an insertion. Insertions are super easy for us. We use the vec, so we push. Replacements are a little bit more awkward. We're going to use replace with a mutable reference to that box, but also that lens position. And then we're going to use our lens. So this is going to swap the lens in for us and then return the old value. And we don't care about the old value, so I use an underscore. Again, mutating, so we don't need to do anything else. Everything there is done. And then we take the boxes that were filled with that fold, we iterate over them, we enumerate to get the box position, we flat map because the interior boxes of lenses that we're iterating over, I don't feel like collecting, and flat map will flatten the iterator for us. We go into it or enumerate again to get the position of the lens. We have to add one to the box position and add one to the lens position. And then we have to multiply by the focal length as well. And that is our return value. We sum that into a U size and we are done. So we can bench this. I'm not anticipating it being super interesting. Looks like we're getting 50 microseconds for part 1 and 276, we'll call it, for part 2. One interesting thing is that there is now an alloc profile in Devon as of, I think, 1.6, 0.1.6. So it's been around for one patch version now. This basically does a similar thing and doesn't really, as far as I can tell, affect timings. So if we go to our benchmark and at the top, we stick the global allocator in here, we're going to pull in the alloc profile. This is kind of the same setup that we do for Devon, or not Devon, DAT, but it's much less sophisticated is kind of the wrong word. It just does less in general. So we need to go to our root, look for Devon, upgrade, and then when we run, we get allocation information. So in this case, it's saying that we ran in 50 microseconds and we allocated 8 bytes total. And our other one is 273 microseconds, allocating 120. We deallocated 220. And I'm not sure how to interpret grow yet, but interesting to have more information here. So let's compare that with DAT. DAT is saying that we got 1 kilobyte in 3 blocks at total, 1 kilobyte at heap max, and 1 kilobyte at heap end. Interesting that the numbers are a little bit different. I did see bench values in here. I am not sure if we need that. I don't see it in this first one, so I'm inclined to say that we don't need it. Either way, interesting to see that there's a difference here. So this is an alloc of 8 and a dealloc of 8 bytes versus what is effectively the base for everything that I've ever seen for DAT. DAT seems to have, or DHAT, I actually don't know how to pronounce it, seems to baseline here. So if we say that 1088 is the baseline, then this is 8 bytes. And of course, if we pull the DAT heap in, we'll see a little bit more data. And we've got 8 bytes registered here for part 1 main, process, 2-string, display for U64, because we do run 2-string for everything that we return. And this is standard out, write format, 64 bytes there. And this is the allocator itself, 1 kilobyte. This is actually probably printing to standard out and acquiring the lock. So not worried about this, not worried about this. I think this is really our application. And if we run that on part 2, we get 320 kilobytes with a Gmax of 126. See how that compares. About 120. The numbers are pretty different here, and I'm not sure why. So we've got alloc, dealloc, and grow, and DAT is telling us that we had 320 total, and at our heap max, we had 126. So the numbers are a little bit different. I'm not entirely sure why. Our baseline is basically printing out this number. So our baseline is about 1,000 or 1 kilobyte, whereas DAT is only running this on the benchmark. So there will be a difference there. That's why we only see 8 bytes here, but we see a kilobyte in DAT because DAT is doing our binary. And if we look at our benchmark, it's just the process function. But if we look at our binary, that involves pulling the string in and opening standard out to write. So slight difference in terms of what we are actually measuring here, which is interesting to note. I don't see how that would account for the difference here. So 320 and 126 and 2,247. So looks like we're getting approximately the same amount of blocks. The numbers look a little bit different to me. I'm not entirely sure why. A little bit more investigation to do there, but very cool to get numbers out of Devon as well. Of course, as we do this, the numbers are starting to dwindle a bit. We've got, as of 2 hours, we'll say, after the problem, we've got about 10,000 people who have completed. The private leaderboard has a new person ranking in third, gold armor or oro armor, along with looking for an internship and a fellow. Very much the top sort of like 6 that we're used to seeing up here, top 7 that we're used to seeing up here. And a decent amount of people are, I want to say like somewhere between 30 and 50. So 40 something have done part 1 and part 2 for every day so far, which is amazing. So that's it for today. I hope you enjoyed Len's library, and I'll see you in the next one. Have a great rest of your night.